Let me start the talk by introducing you to the very interesting phenomenon of distractor intrusions. Imagine that you're looking at the screen and you see a stream of letters and digits flashing one after the other. Your task is to detect and report the digit inside the square. So letters are completely irrelevant. Many studies have shown that we're surprisingly good at attending and reporting this kind of target, even at very high speed. In this case, in a study from our lab, each frame appears for 50 milliseconds, yet accuracy is about 80%. However, all it takes to ruin this high accuracy is to change one small detail. If you change the stimulus that follows the target from a letter to a digit, accuracy drops from 80% to about 40%. And why? Because the rest of the time, people report seeing the wrong digit inside the square. So this phenomenon is called distractor intrusions because the irrelevant distractor intrudes into our consciousness. How can we explain this finding? Well, an important but often neglected fact about attention is that it's not an all or none phenomenon. It's a dynamic response that develops over time. And importantly for us, it lingers even after the target disappears. This was first suggested by Reeves and Sperling. They suggested that following a target or a cue, attention behaves like this: a transient attentional response that quickly reaches a peak and then dissipates. The period of time between the onset and the offset of attention can be referred to as an attentional episode. We use the term attentional engagement to refer to the peak of the attentional response. Surprisingly, only a few models adopted this perspective. But for us, this is crucial, as it explains why the distractor is encoded even though it appears after the target. It's simply shared in the same attentional episode as the target. Now, this alone cannot explain why the target is seen on some trials and the distractor in others. There are only a few accounts that try to address this issue. The first account suggests that distractor intrusions occur only when attention fails to engage in the target. The second account suggests almost the opposite. The distractor intrusions reflect intact attentional engagement, and that the selection between the target and the distractor occurs only at the post-attention stage. Finally, we suggest that distractor intrusions occur because of a delay in attentional engagement. This account is based on previous work suggesting that engagement occurs only after sufficient information about the selection feature, in this case the square, has been accumulated. When detection occurs rapidly, attention is going to be correctly engaged in the target. However, detection is affected by various factors that introduce temporal variability, like perceptual noise, expectation, alertness, so information accumulation can take longer. Any delay to detection will lead to a delay in attentional engagement, which means we might engage in the wrong digit. So we have a very interesting situation where three different theories can all explain the same findings. To differentiate between the three theories, we turn to event-related potentials, and specifically to the N2PC component. So what is the N2PC? When a target appears on one side of the screen, we see an increase in neural activity in the opposite side of the visual cortex. So when we record the electric potential from two electrodes, ipsilateral and contralateral to the target, we get these kind of waveforms. And when you subtract one waveform from another, we get this difference wave. And the additional activity we see in the 200 millisecond window is called the N2PC. Importantly for us, previous work connected between the N2PC and either the onset of attentional engagement or a process that immediately precedes attentional engagement. Therefore, we can use the N2PC as an index to whether attention was engaged, and importantly, when it was engaged. The N2PC is extremely helpful because in this case, it can help us differentiate between the three accounts. First of all accounts agree that on trials where participants choose the correct target, there should be an N2PC. But what about intrusion trials? Well, if intrusions occur due to a failure to engage, then there shouldn't be an N2PC. If intrusions occur when attentional engagement is intact, then the N2PC should also be intact. And finally, if intrusions occur when attentional engagement is delayed, then the N2PC should also be delayed on these trials. So in the first experiment, we used the same paradigm you saw before, and split the data based on the response. First, when participants were correct, we can see a clear N2PC between 200 and 300 milliseconds. And for intrusion responses, there was still an N2PC response, but the onset of the N2PC was delayed. So this is all the time I have to talk about this finding, but if you're interested, the article is now online. Following the first study, the second question we wanted to ask was, what happened to the target? That is, on trials where participants reported the distractor, what was the fate of the target? One option is that the target was encoded in working memory, but was not reported. So even though both items were encoded, the distractor was mistaken to be the target. The other option is a bit more radical, as it suggests that the target did not gain access to working memory. In the fourth experiment, we simply allowed participants to have 2 guesses regarding the identity of the target instead of 1. For the first response, we can see that the behavioral results replicate. Next, we examined the second responses. Specifically, we focused on trials where the first response was already a distractor intrusion. Our main question is, what is the likelihood that the target is reported as a second response on these trials? So what are the options? In the worst case scenario, if the distractor's encoding and the target's encoding are mutually exclusive, then participants should have no information about the target on distractor intrusion trials, and accuracy should therefore be at chance levels. What is the best case scenario? Well, we wouldn't expect 100% correct responses, so reasonable comparison is that accuracy in the second response will match the accuracy in the baseline condition. If participants generally can encode both items, this should be their accuracy level. What do you think happened? Well, it was in between. Higher than chance, but far lower than the best case scenario. That means that we fluctuate between 1 item and 2 items, and also suggests that the competition between the target and distractor reduces the likelihood that the target will be encoded. In the final experiment, we asked the following. Perhaps the target is encoded in working memory, but is then dropped from working memory because it is deemed to be irrelevant. To answer that, we once again measured event-related potentials and once again allowed participants to give 2 guesses about the target's identity. So first, let's look at 2-item trials, that is, trials where participants reported both the target and the distractor in whichever order. So this is the average waveform. In the 200 to 300 millisecond window, we can see the N2PC. But more important is this later amplitude. This is called the CDA. And why it's important here is because that the CDA amplitude gets larger the more items are encoded in working memory. So now we can ask, what should we expect from the CDA on single item trials? That is, trials where either the target or the distractor were reported. Here are the options. If, for whatever reason, both items were encoded in working memory but could not be reported, then we should expect the same CDA amplitude on single item trials as 2-item trials. A second option, what if both items were initially encoded but then one of them was dropped before the response stage? In that case, the CDA amplitude should be the same early on, indicating encoding, but then split into 2 later, indicating that the item was dropped. Finally, third option, if one item is blocked from entering working memory, then we should observe a difference in the CDA from the earliest time window. And what do you think happened? First of all, it's clear that the amplitude of the CDA is different overall. So that canceled out the first option because it shows that the number of items in single item trials was indeed lower than 2-item trials. Second, if we look at the earliest time window between 400 and 500 milliseconds, we can already see a difference in the CDA amplitude. So this suggests against the idea that both items were initially encoded, leaving us with option number 3, meaning that on some trials the item was blocked from entering working memory and that this competition was resolved early on. To summarize, I'm going to show you a sketch of what we think is going on, and how we think that fast and slow engagement affect perceptual outputs. On top, we see the visual inputs. On the left, we see the sensory representation. After about 50 milliseconds, the visual input from the target reaches the visual cortex. From there, processing proceeds in a feed-forward fashion, until information accumulation about the selection feature reaches an engagement threshold. At that point, an attentional episode is triggered, and this kickstarts recurrent processing that exponentially enhance any representation in the visual cortex. At the end of the attentional episodes, some representations are usually going to be sufficiently activated to be encoded. However, the most strongly activated representation is going to be perceived as co-occurring with the selection feature. In this case, because the engagement threshold was crossed early, after about 150 milliseconds, both items were encoded, but the target was correctly perceived to appear alongside the square. On the other hand, if attentional engagement starts late, it enhances the distractor more than it does the target, which can mean that either both items are encoded, but the distractor will be perceived to co-occurring with the square, or even more extremely, only the distractor will be encoded. In conclusion, we suggest that the speed of attentional engagement is inherently variable, and that this variability is not just a nuisance to be collapsed over. Instead, it is associated with our perception, such that slower engagement corresponds with distractor intrusions. And perceptual competition that occurs prior to encoding between a target and a distractor that appear in the same attentional episode can determine which item or items will gain access to working memory. I want to thank my lab, my mentor, the British Academy, and thank you for listening.